With each fascinating picture captured by the James Webb Space Telescope, it keeps on gathering contemplations from various corners of the universe, including planets within our own planetary system. A year earlier, we thought about our most significant deep-sea pictures showing the Kina Nebula, the Saint Quintet, and additionally the strikingly enchanting Deep Field image. This express picture clearly depicts different galaxies resting in the vast extent of the universe, fulfilling the doubts made. The James Webb Space Telescope hasn't stopped being amazing. It has in fact uncovered objects that test deeply grounded cosmological hypotheses. These astonishing revelations are now being named universe breakers by cosmologists, frustrating established experts with their ability to challenge existing theories. The reasons for these discoveries remain shrouded in mystery, throwing our theories and hypotheses into disarray. So what's the latest scoop from the James Webb Space Telescope? What remarkable new discovery has it revealed that was previously unknown to us? Join us as we dive into the revelations of how the James Webb Telescope has presented evidence proposing the presence of another universe, testing the standard understanding of the Big Bang. Our universe, as we've long known it, arose from a hotter, denser state by means of a theory known as the hot Big Bang. This thought, a significant scientific achievement throughout the past century, gained overwhelming support during the 1960s with the discovery of the cosmic microwave background CMB and echo from the early hot and dense state. Over time, the Big Bang has remained the leading theory explaining the origins of our universe. All things considered, new and fundamental insights have led cosmologists and astrophysicists to re-examine both the ongoing expansion and the Big Bang itself. Despite these challenges, alternative theories have failed to gain traction, with the prevailing theory of the universe's origin enduring. According to the dominant view, the universe began as a smaller, denser entity in the distant past. The presence of radiation such as photons shows that the universe was hotter at its beginning and has since cooled. Extrapolating backward in time, the density, temperature, and energy levels varied where a singularity could form, and the laws of physics would break down around 10^3 seconds. In such a short span of time, microscopic distances, short timescales, and high energy levels challenge our understanding. Rewinding the cosmic clock to the speculative 0 point, if the universe began as hot and dense, it would have expanded and cooled, producing vast amounts of particles and antiparticles, with excess particles being destroyed by radiation as temperatures decreased. The breakdown of the electroweak and Higgs forces led to the formation of the four fundamental forces and particles with non-zero masses. As the universe cooled further, protons and neutrons formed composite particles called quarks and gluons. The combination of protons and neutrons led to the formation of light nuclei such as deuterium, helium-3, helium-4, and lithium-7. Overdense regions underwent expansion due to radiation pressure, followed by gravitational collapse, leading to the formation of large-scale structures. About 380,000 years later, the discovery of the cosmic microwave background many years ago established the theory of the Big Bang as the most supportive explanation for the universe's creation, describing the early universe as a hot, dense soup of subatomic particles gradually cooling over time. The Big Bang versus steady-state theory. While most cosmologists and astrophysicists embrace the Big Bang theory, staunch defenders of the steady-state theory, such as Fred Hoyle, continue to support increasingly doubtful ideas, only to face defeat in the face of overwhelming evidence. The proof presented was conclusive. It wasn't dimming starlight or reflected heat from dust. The celestial glow displayed remarkable consistency, resembling a perfect black body, yet had no connection to known objects in the universe. Despite this, Hoyle and his allies continued to undermine scientific progress by backing scientifically dubious ideas. Meanwhile, the fields of space science and cosmology underwent significant changes from the 1960s through the 2000s, with cosmology making particularly vital strides. We mapped the universe, described its large-scale structure, and examined the evolution and dynamic interactions of galaxies and their stellar populations. Yet even with these advances, we encountered anomalies that challenged explanations within the framework of the Big Bang theory, most notably the absence of predicted relics such as magnetic monopoles or particles from grand unification, which led many to reconsider aspects of the theory. The universe we observe today seems to require forces beyond our current understanding. Despite these challenges, the expansionary model persists, while existing theories fail to account for observed anomalies. Two approaches have emerged: refine current theories or consider alternative explanations. The theory of inflation has emerged as the most promising framework for extending the Big Bang viewpoint. Inflation suggests a brief period of rapid expansion that smoothed the universe, giving it uniform properties. It addresses the horizon problem and predicts the development of quantum fluctuations which manifest as density and temperature variations. The predictions of inflation align with observed patterns and changes, reinforcing its validity. However, despite alternative theories, inflation's scientific strength remains unmatched. James Webb Telescope's amazing discovery. Astronomers quickly noticed anomalies in the images sent by the James Webb Space Telescope starting in 2022. These revelations could require a reassessment of key aspects of the universe's origins and development. One major discovery made by the Webb telescope was the presence of fully developed galaxies much earlier than predicted by the standard cosmological model. This anomaly challenges the established sequence of events following the Big Bang, where stars and black holes form, first followed by galaxies. Such discoveries disrupt our understanding, like encountering grandparents depicted as children in a story. Furthermore, later evidence has revealed irregularities within major theories of the universe, such as the persistent error in determining the Hubble constant, which continues despite improvements in data accuracy and measurement techniques. New data from the Webb telescope presents challenges to the current cosmological model. These issues highlight imperfections within the model, raising questions among researchers and physicists. While the model has undergone changes recently to align with emerging data, some argue that these changes have been too accommodating. As a result, there is growing recognition that a change in perspective may be necessary, possibly reshaping our understanding of the universe's fundamental properties. The telescope's discoveries may not only answer some of the most profound questions about the origins of the universe, but also raise new questions that could lead to even deeper and more revolutionary insights. We may be witnessing the beginning of a scientific revolution, one that could change our understanding of the cosmos forever. As the James Webb Space Telescope (JWST) continues its mission, its discoveries are raising profound questions about the nature of the universe. The anomalies it has uncovered, such as the presence of fully formed galaxies earlier than expected, unexplained cosmic structures, and inconsistencies in the Hubble constant, suggest that our current models may be incomplete or even fundamentally flawed. These findings have led scientists to reconsider long-standing cosmological assumptions. If galaxies formed much earlier than predicted, what does that imply about the sequence of cosmic evolution? If the Hubble constant is inconsistent across different measurement methods, does that mean our understanding of the universe's expansion is incorrect? These uncertainties have fueled speculation about alternative theories, including modified gravity variations in dark matter behavior and even the existence of a multiverse. One of the most controversial but increasingly discussed implications of the JWST's discoveries is the multiverse hypothesis. If our universe does not behave as expected, one possible explanation is that our universe is just one of many, each governed by slightly different physical laws. The multiverse theory suggests that countless universes may exist beyond our observable cosmos. These universes might have different physical constants, different types of matter, or even different dimensions of space and time. Some scientists argue that the anomalies observed by JWST could be signatures of interactions between our universe and other universes. For decades, the lambda-CDM model, lambda cold dark matter, has been the prevailing theory of cosmology. It explains the universe's structure, expansion, and evolution based on the Big Bang, cosmic inflation, dark matter, and dark energy. However, JWST's findings are putting pressure on this model, as certain observed structures do not align with lambda-CDM predictions. For example, the existence of mature galaxies in the early universe contradicts the idea that galaxy formation takes billions of years. The Hubble constant discrepancy suggests that our understanding of cosmic expansion is incomplete. Dark matter and dark energy remain elusive despite being essential components of the lambda-CDM model. If the lambda-CDM model is inadequate, then scientists must explore alternative explanations. Some researchers propose modifications to Einstein's general relativity, while others investigate the possibility that our observable universe is just a small part of a much larger cosmic framework.